Hello. Okay. So, I guess quick recap of last time. We implemented the Atom optimizer, which is, as far as I know, the state-of-the-art modification to stochastic gradient descent that people actually use. It's really simple. This is the whole thing. It's really similar to what we were using before, which used velocities, and the gradients updated the velocities, and then the velocities updated the parameters. Instead, we have two moments. So I think it's like the first derivative and the second derivative, basically, or the speed and the acceleration. And those two together decide how to update the parameters instead of the gradients directly. So that's basically what we did last time, in addition to fixing the softmax, which we had already done before, already implemented but wasn't working properly before. So the agenda for today is implement tensors. What is a tensor? So a tensor is a generalization of a vector or a matrix. So a vector is a column, or I guess it's a list of numbers. A matrix is, you could say it's like a two-dimensional list of numbers. The tensors that we care about today are going to be three-dimensional lists of numbers, and a tensor in general could be more than three. So the reason we're doing this is transformer architecture. Images. The reason is that we're implementing this. Reminder that well, actually, let me pull that up. Decoder only transformer. We're going to start and possibly end with a decoder only transformer, which is simpler than the full transformer, because here it just looks like this. So we don't need the left side. We don't need the left side. This is the encoder. And we don't need this middle piece where we take input from the encoder. So the network becomes simpler. It's just these decoder blocks. The important, or the only thing that we're missing from this decoder block is the attention mechanism, which looks like this internally. You can implement it as a single step, or you can implement it as a combination of these things, and I'm going to use a combination of these things because I already have softmax and linear implemented. So matmul is the new thing that we need, and matmul is not compatible with the way we're inputting our samples right now. So right now our samples are a column vector that includes both, this is like a 1 by cars times alphabet. And this is like a, or why don't I say cars times alphabet by 1. This one is cars times alphabet by batch size. And this one is going to look like this. Alphabet will go first, actually. Not that it matters. So what we've been doing so far is in the input layer of our network, we stuff a huge column vector with all of the letters of the prompt, and we're just stacking vectors. For each letter of the prompt, we stack a new 87 dimensions into the vector. And then when we're doing batches, we have this column vector. So each column vector is a sample, and then we have a matrix that is a batch of samples and which is a batch of samples. So the cool thing about this is that when we added this extra dimension for batch, when we do all our matrix multiplication and stuff, each batch is kind of independent. And then at the end, we end up with a bunch of independent activations. And then when we do the backwards pass, we end up with a bunch of independent gradients. And then we just sum them together. So here we're taking it a step further, and we're going to say every single letter in our prompt is independent. We're going to do independent processing on every letter and every batch. So it's kind of like you've got two batch dimensions, really. And the obvious problem that you are going to run into if you do this is that now the network's not able to take advantage of the fact that it knows more than one letter at a time. Because we've isolated all of the letters in the processing. However, this matmul layer, which we're going to implement after we adjust our current layers to be able to handle tensors, this matmul layer is going to be combining together. How do I say this? It's going to do a matrix multiplication between different token sequence, like between faces of this block. So we're going to matrix multiply, which is going to combine together the tokens and the sequences in the output. So now the output it kind of knows stuff about all of the tokens in the sequence at the same time. So basically, we're going to change our architecture so that all of the letters are independent of each other. And then we're going to add in an operation that mixes up the letters in the sequence so that we get back information about the letters. But we're in a lower dimensional space, which I don't know how important that is. Because we'll have fewer parameters per letter, and then we're using the same parameters for all of the letters. So maybe that's an advantage in terms of computational stuff. Or maybe it's a disadvantage, and we're going to have to boost the number of free parameters to compensate. I guess we'll see. Okay, so that's the intuition. So now I'm going to go through our existing code and try to make it so that you can have so that it would work with 3 tensors at least. And I think I'm going to see if I can make it work with an arbitrary number of dimensions while I'm at it, so that I could still pass in stuff that looks like this. And I could possibly pass in stuff with even higher dimensions. So let's see how that goes. And let's get started. So let's just go through our layers one by one and see if we can update them to care about the dimensionality, or to handle higher dimensional stuff. Hopefully to not care about the dimensionality of the inputs. So none of this matters. In the linear layer, we still should be using a matrix. We shouldn't be using a higher dimensional tensor, because we're treating each token separately, or at least that's how I think it works. If I'm wrong about that, then everything that I'm going to do today is going to be wrong, but hopefully I'm not. We'll see. So the weights and the biases should be the same. Forward should be different. Okay, so first of all, I think I might not need to do this thing that I'm doing. So I'm copying the bias vector into a matrix so that I can do plus b. But I think if I just did plus b, it would already broadcast it to all of the columns in the matrix. So let's see if that works. I'm going to do a few things to make the test go faster. So I'm going to say I only care about, that's obviously not how you write that number. I only care about the first 10,000 samples in my training. I'm going to make this network a lot smaller. What's a good power of 2? Is 54 a power of 2? Okay. I'm going to change the number of characters to just be 10 instead of 20. And then I'm just going to confirm that everything still works. (23, 30, 32). That looks like it's working. Like, I guess I would have expected a crash if it were not working. And then I'm just going to go and put this back to how it was and make sure we still get, make sure that that grows around the same rate, 23, 30, 32. (22, 28, 30). Okay, about the same. So we don't need to do this anymore. It made sense, but we're already broadcasting by doing this, and now this should, now this doesn't care about the size of the input anymore. However, this does. So instead of doing a matrix multiplication, well, I guess, why don't we test this? I think matrix multiplication is not going to do what we want, but let's see. Python, numpy.nd array, or just array, 1, 2, 3, 1, 2, 3. 1, 2, 3. So this is going to be... No, this is just a regular matrix. I want a 3 tensor. How do I make a 3 tensor? I guess I need a third square bracket, and maybe I need to repeat this part. I don't know where the non-printable character is. Okay, from NumPy, or import NumPy as NP. This looks like a tensor, so let's say x is this. X.shape should have 3, okay. So, let's do a matrix multiplication. So, W equals NP dot array. 1, 2, 3. This should be 2-dimensional. 1, 2, 3. 1, 2, 3. W matrix multiply X. Okay, this is perhaps exactly what we wanted. It's a little bit hard to tell. Clear. W, X, W at X. So I'm just trying to picture a cube. I'm trying to picture each of these matrices going behind the other one. And then I want the columns to all be how do I say this? It's like you multiply 1 by something in the column, 2 by something in the column, 3 by something in the column, and then the result is the location. The result goes into a location in the output matrix. And that kind of looks like what it did. So I think this might actually already be working. Where was I? Yeah, I think this might already be okay. It's going to be a little hard to test. I guess the way I could test it is by adding a second batch dimension temporarily. So sample batch. right? So if I did this, so let's go to our data loader. Well, okay, actually, one thing at a time. Let's get it so that it still works, but it might work in the new way. And then we'll test the new way. Okay. So that's the forward pass. The backwards pass, we do delta. So potentially this works also. D is an order 3 tensor. A is an order 3 tensor. So these potentially still work. This one's not going to work because I'm summing along only one axis, but I want to sum along all of the axes. Except 0. NumPy sum all axes except. So I can pass a tuple of axes. But I'm thinking I can probably do it with einsum also. Yeah, this is what I was looking for. Okay, so this would look like this. Biases is D for np.einsum D dot 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 or I dot 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 goes to I. So sum along all the axes except the first one. Does this work? No. Output has more dimensions than subscripts. That's because I want to sum along all the rest of them. Yeah, I'm doing this. I'm doing literally this, so why doesn't it work? np.einsum I goes to I D or X. So Google's just wrong? You can't do it like this? away. Einsum ellipses. I don't get it. You can't just add the ellipses here, because then it's going to have the wrong shape. Because if I had done IJK, then I get what I want. I just don't want to have to say JK. Is this doesn't seem to be the same issue. Oh, no. Yeah, I don't know. I mean, would it work if I put the ellipses before the I? No. Okay. I mean, it wouldn't have given the right answer, but I'm just curious if it would even work. I wonder what optimize is. I don't know. What if I provide more letters than I needed? IJKL. It says that's too many. But I can't just say like ... to get the rest. Ugh. NumPy. I don't know. I'm not even sure what to search for anymore. I don't want to. No, this is wrong. Blah. This should work and it just doesn't. So I don't think I can make it as general as I wanted to. I mean, this looks like it works. Like, why does it not work when there's only one input? I want to sum over all extra dimensions, but I'm getting the error above. That's what I'm doing. So AI does not know the answer. Don't know. What if I don't know how many dimensions the input is? Yeah, this makes sense. This makes sense. So back to like this. One to as many as there are. One to a.ndim. So skip over the first one, sum over all the others. Yeah, that's working. I wonder what the optimize thing is. So this looks like it's working. Let's go back here. Optimize equals true. There's no way that makes a difference. That's a totally different kind of error. What if I just open up Python? Declare my x again. Import numpy as np. Declare x. Einsum. Optimize equals true. Then it works. What is optimize equals true doing? So if I have a difference, what version of NumPy am I using? How do I check that? Two point 3.3. 2.3.5 is the latest. Okay, I think I've literally found a bug in NumPy, which is crazy. So I'm going to make a reproducible script. All right, save this for later. So what does this mean for us? We can't use the einsum. This seemed to work. Optimize equals true. I actually don't know why this caused a different error, because this should be doing the same thing as before. Oh, I think this is just the wrong, it should be a column vector, but I was, I need to reshape it basically. Dot reshape self.bias dot shape. It's called biases. Okay. So I don't know which of these is better. I'm gonna go with the one that seems to not have bugs. These both work though. I don't know if the optimize thing makes sense. All right, so that's linear. Good. Let's check that off. So next up, layer norm. Gamma and beta should be the same. Saving and loading should be the same. Forward and backward will be different. So X is now a tensor. These are the same. Summing and doing stuff over axis 0 is what we want to do, because axis 0 is the token axis, or the sample axis, or whatever. It's the axis with the stuff that we care about. Variance epsilon. X is a tensor. We're subtracting and broadcasting this column to everything in the tensor, so this should still be working. This is a vector, so we're broadcasting it here as well. This is a Hadamard product, so that should be the same no matter how many dimensions are in X hat. This should be broadcast as well, so the forward should already be working. Backward. This is a vector. This is a 3 tensor, or more, or less. Hadamard product. These are also tensors, DNA. So Hadamard product, good. Regardless of the tensor or anything. The 0th thing is the sample or the token, so that's right, or that's fine. This should be good. So this is a Hadamard product. This should be broadcast to a tensor. This is a tensor. Then we're subtracting a column vector. So axis 0, axis 0. Okay, so this all looks good. Now I can see some problems here. So delta is going to be good. Gamma and beta are not going to be good because we're summing along only one axis. But I want to sum along as many axes as I need to. So that is just this. We'll do the same thing over here. Okay, so layer norm should be working. With both matrices and tensors now. Still working with matrices. So, layer norm done. Softmax. Activation functions, these should be fine because we're already broadcasting everything. So the Hadamard products are fine. This is really weird syntax, but this is it's fine because we're just doing the same function across everything. Softmax. Okay, so X is going to be a tensor. Hadamard product is fine. Along axis 0 is fine. Along axis 0 is fine. So forward should still be working. Backward. Okay, we are defining the Jacobian, which we're defining as a 3 tensor, but it's going to be a 4 tensor if S is a 3 tensor. So instead of having B here, I think we can just do ellipses. So basically go along all of the extra dimensions. Does this still work? Huzzah! Okay, I think that's it for softmax. None of this should care. None of this should care. So, so that's it. Now we just need to test it with inputs that are 3 tensors. So, data loader. I wanted to be able to well, I guess we don't have to do that now. I was going to say I want to be able to swap in different data stuff. Like I could do mnist. But then I would need to change this thing. But that would be fine. Okay, maybe we take the time to fix the way we load data while we're at it here. So one problem is that the one problem is that we're loading data outside of the load function. So if I were to import both data loaders, I'd be loading both data sets, or at least I would be loading this Final Fantasy data set, even if I don't use it. So can I change that? The issue with that is I need a list of the characters in order to make the vectorization functions. But I could just throw an exception if they have not loaded yet. So let's just do that. Don't do this out here. Do this in here. Global all characters. If not, all characters, raise exception, data not loaded yet. Do that over here. Okay. To do, what if it's a softmax output? I don't remember what this to do means, but we know that softmax, we know that that's working fine. I'm just going to delete that. I don't know. Oh, I guess we just, you have to argmax it after, or you have to pick one before you unvectorize. But we're already handling it somewhere else, whatever we meant. Okay. So this should still be working now. And we've delayed loading until you actually say load. Okay. Now, what if I add no QA here, and I do from mnist data loader, import data loader as mnist data loader. Add a no QA on that. And try just, so this is not going to work because my network's not going to be the right shape. The output needs to be 10. The input needs to be 28 by 28, I think. By 28. And the output should be 10. No way, it still works. 90%, 92. So I'm curious now, with all of the improvements we've made, And I don't know what a good value of lambda is. But I think it was lower than this. How good can we actually get the network to be? So let's replace the 64s with, I don't know, 512. This will be very slow. But we have a bunch of stuff we didn't have before. Layer norms, skip layers. I guess that's it, actually. No, and Atom. I guess this will probably take a long time. Well, while that's running, let's figure out trying to think of how I want to do this. I might want to just duplicate this file and this one could be, how would I call it? It's like tensor data. So, wow, 96% after the first epoch. So after a minute and a half, we're higher than we were able to get before without convolution. That's really cool. Okay, so now this is an alternative data loader. Oh, wait, how long has this been here? This doesn't need to... have any reference to MNIST when we're loading the Final Fantasy data. All right, so vectorize needs to be different. So it should actually be two-dimensional. So this one should look like, and I've got 87 hard-coded all over the place. When this should really be len of all characters. I should do the same over here. Add the exception here. Okay. So this is, the length should be the am I trying to say? What is text here? Is the, okay, so add a comma here. The first axis is the character. The second axis is the number of characters in the prompt. So this should have a comma. I don't know why we bother reshaping. We shouldn't have to reshape. Why do we reshape here also? Because I can just do comma 1, right? 97. 97.5 without convolution. Anyway, let's stop this, and then this will crash it. Yes. Clear. Go back here. Let's go back to using the other data loader, not MNIST. And I don't need these to be 512 because I want to go back to just checking if stuff works. So you can be 64. Okay. So that needs to be a tuple, not just two parameters. And same over here. And I shouldn't have to reshape. If this works, I'll kill it and try again without the reshaping. This is still slow. Why is it so slow? Oh, because I didn't put a limit on the number of yeah, give me the first 10,000. %50 on the first. Oh, I guess that's an architecture we haven't actually tried yet, so it makes sense. Okay, the first 10,000. So this should be fast. That worked, which is good. We check if it works again now that I am not reshaping it, because I don't think I should have to reshape it. Good. Then the tensor version is I don't want to do I times. I just want to take the, how do I do this? The I think it would be this, comma this. Or actually, this would just be I. And then if we make the output be similar, then you would do well, this part's kind of completely different. So you have your text, and then I would just iterate over the axis number 1. And I don't need to do any kind of division because it's just one letter per, or one token per whatever. I guess I should call this J, call this I. If I comma J, this looks right to me. Yeah, this looks right. Okay. Okay. So let's try it. Load the tensor version. And then don't do times characters. I guess I never, yeah, I guess you just don't, you never do times characters if you're loading the tensor version. And the output is still just one letter, which means unvectorizing there should only be one J, but that's fine. Hopefully I just screwed up something around here. Where did it fail? The output minus the expected output. The output was 87 by 500. The expected output was 87 by 50. Where did 500 come from? Maybe I should go into I should print the shapes of the activations as we go, just to understand what's going on. And I can do that here. Print x.shape for x in xs. Where are we getting 500? We're getting 500 right off the bat. Maybe my tensor loading. Or something. Oh, wait. I expect this to be 3 dimensions, but it's only 2. So now I'm thinking it's wherever I turn stuff into batches. Batch size 50. Go here. Batch. Also, just I'm just gonna call this batch size. I'm gonna get rid of the word mini everywhere. Okay, but here's the issue, probably. Okay, so we grab a bunch of examples, and that becomes our batch. Then we're trying to make a tensor out of these batches, but we're using hstack. What is the right way to do it? NumPy make tensor out of matrices. Stack, and then you can say an axis. So x equals numpy.stack. Axis equals, and I just want it to be like, I want it to be dstack, but I want it to be stack of whatever the next thing is. NumPy stack new axis. Oh, so if I just don't specify an axis, it should do it. So if I just get rid of the h, it should do it. It put the axis at the beginning. I want it to come at the end. Does stack -1 do what I want? So if you do axis 0, it becomes the first one. Axis 1, it becomes the second. Axis 2, it becomes the third. Axis -1 doesn't show me an example. So let's just try it. It is putting the 50 on the end. Okay, and then the first layer is having a problem. Gamma is 87,1. And it doesn't know how to broadcast that. I thought it would know. Because I'm doing -1, but I want to do as many as I need. I don't know how many I need at this point. I'm gonna have the same problem with the other. No, I guess with the matrix it should be fine. What if I just don't add the -1? Does that make it easier for it to figure out how to broadcast? I guess not. That's too bad. Okay, so when we go forward, self.gamma.reshape self, how do I say this? I just want it to be this, and then as many ones as I need. This is very annoying to write. Maybe I can just reshape it to X. No, it doesn't know how to add the extra stuff. NumPy reshape add ones. New axis or expand dims. Yeah, how do you do those things? You slice and then you add a new axis. Expand dims -1, that's the same thing. Reshape and then shape and then you add 1. I want to add enough new axes to match a different matrix, a different tensor's shape. I really got to do this thing. What is this? Yeah, okay. You just have to multiply it by needed dims. I wish there were a less weird way to do it. So while self.gamma.shape is less than x.shape, expand dims. How does NumPy expand dims? Can you do that on an object or? New axis? by.new access. So once we learn how many dimensions our input is, we expand gamma and beta. And then it looks like all the other stuff we did worked. This was the only one that didn't, which, I don't know, I guess it seems weird that this is the best way to do it, but I guess the other things we did just didn't need it for whatever reason. This is going slow. This is going a lot slower than before. Why? It should be going... No, I guess it... This linear layer... I guess for the same size network, it should be going slower. Because I'm... Well, I don't know, actually. I don't... Because the matrices should be 10 times smaller. Like more than that. Because I'm not doing times 10. Okay, well that's already reflected in the fact that I made this smaller. All right, so for the same size network, it should be slower. And then I was able to reduce the size of the network in the input layer. But apart from that, it makes sense that it's slow. And then it should also not do a good job because every letter is basically independent. So actually, so in the end, it's going to give 10 different predictions. It's basically 10 different, how do I say this? I'm doing single letter predictions 10 at a time. This is so confusing. It's taking so long. I guess these layers should be 10 times slower. Hmm. Um, so now I'm wondering if we're keeping this tensor activation all the way through the network, how do we get a single probability out? It's like this linear layer maybe is different from the others, because maybe you're taking the whole matrix and linearing it into a vector. Or maybe I don't know. I guess I don't know when you switch from I don't know when you switch from token sequence back to just softmax vector. Is it in the final output, or is it somewhere in the middle? It seems like it can't be inside here, because then you would not have a vector. You would not have a sequence, a token sequence matrix into the next attention block. But if it really is in the linear layer at the end, I guess I don't know why you only have one linear layer. Wouldn't you want to have a whole feed-forward network to be able to learn as much as you can once you're combining the two axes together? And then why is it not explicit that this is like broadcasting from a matrix to a vector? Yeah, I don't know. Curious. Annotated transformer. When people do this in PyTorch, what does the output linear layer look like? Where's the where's the output? I don't know how to read this. I'm not familiar enough with PyTorch. Does encoder decoder have the linear and softmax at the end? I don't know. Where are we even doing a softmax? In attention. Generator. So is this the end here? Linear plus softmax generation step? I don't know. I'm confused about this. How about the even more annotated transformer? This is hard for me to understand also. I'm wondering if I was just wrong about this. It's hard to tell what is an input in these. What is the shape of the input and what is the shape of the activation at each step? What is the shape of the activation at each step of a decoder only transformer? Any chance that someone can explain that to me? Okay. the input is batch size, sequence length, embedding dimension. That's what I expected. After self-attention, it's still the same. After the feed forward step, feed forward network, it's the same. The output shape remains the same before being fed into the next decoder block. Is it going to tell me the same thing? Maintains a consistent, okay. And then final output layer. The final activation is passed to an output linear layer, unembedding layer, to produce a probability distribution over the entire vocabulary. Input shape BTD. What were they calling B, T, and D? Batch size, sequence length, model dimension. Okay. Only the last token's output. Oh. So you're saying you really do keep this shape the same the whole time, and then you discard everything except the one thing we care about at the end. But don't we need everything in order to do backpropagation? Or isn't it wasteful to calculate stuff that we don't need and throw it away? Why is this so hard to find a resource that will just explain it clearly? So tokenizing I will get to. Positional embedding I will get to. We really do get a bunch of different output tokens and we only care about the last one. It just seems wasteful. Like, there's no point in doing it for all of these if we only care about this last one. We can convert each token vector in our output into a probability distribution over the token vocabulary. Next token prediction, the LLM pre-training objective that trains the model to predict the next token for every token. But why did we calculate all these other tokens if we only care about the last one? Um, so, yeah, I don't even know how it's comparing the output right now, actually. Right? I guess it's broadcasting and it's trying to get the same output for each token. Over here. Because this is a tensor. This is a vector. And I'm back propagating across the whole tensor. It's just so confusing. Excuse me. So, because how would I do this if I only wanted to backpropagate on the last token? Would I want to say all of the rest of the outputs are correct? Or how would I do it? Because the other thing I can think of is to just change this linear so that it only broadcasts the matrix into a vector. I guess I don't know how to say linear I don't know how to drop all of the tokens that I don't care about. Maybe I would just say all of the columns are correct, except the last one. It just seems so weird. How do I back propagate when I only care about, or why am I generating 1 token per input token? How do I backprop when I only care about the last token? Does einsum have a bug? I think these are the questions for me to try to figure out between streams. And in the meantime, this is doing some crazy stuff because I think it's trying to get the same, like this is not going to learn anything, I think, because it's trying to get the same output for each token because I'm implicitly broadcasting Y, which is my expected output, into all of the sequences of X, of the output activations. So I'm saying unless all of them gave the same answer, which I'm expecting Y, then it didn't work. So I'll be training it to always output the same letter, pretty much, I think. I don't know why it's so slow. I would expect it to be maybe 10 times slower, because we're doing 10 times as much work inside here. But I think it's been running for more than 10 times, 5 seconds or however long this was taking before for the first epoch. With such few training examples. So why is it so slow? Am I right that it's learning to always predict the same letter? All right. That's going to be it for now. And I'm going to try to do some research on this stuff. Hopefully this was helpful. Thanks for watching.